So far whatever we have learned is all about how exactly a reactant gets converted into product. In entire reaction mechanism, the topics that are covered till now always spoke about how exactly a reactant turns into product. But now we are going to talk about the behavior of chemical bonds inside this reactant. A reactant in this chapter in organic chemistry is an organic molecule, right? So this organic molecule basically is made up of carbon and hydrogen. And both carbon and hydrogen are non-metals. Because both carbon and hydrogen are non-metals by nature, the bond that we expect between carbon-carbon or carbon-hydrogen will be a covalent bond. Now this can be a polar covalent or non-polar covalent, but at the end of the day, you're talking about covalent bonds. And how exactly a covalent bond is formed? This is formed due to mutual sharing of electrons. When you are having the electrons being contributed by both atoms equally, the bond resulting is called as a covalent bond. And according to the rules of covalent bond, this bond pair of electrons always should be situated at the center. In case I'm talking about the bond between carbon and carbon, the first carbon will put down one of its electron and the second carbon also will put down one of its electron, and this pair of electrons is called as bond pair of electrons, and this have to be equally shared by both the carbon atoms that are involved in bonding. And this also should be placed at the center of both of these carbon atoms. So this is like according to the standard rules of a covalent bond. But then as we already know, this covalent bond can be of two types based on the electronegativity difference between the atoms involved in bonding. For example, instead of carbon-carbon, if I talk about the bond between carbon and halogen, out of these two atoms that are involved in covalent bonding, halogen is more electronegative. Because halogen's electronegativity is higher, it has greater tendency towards the carbon's electrons, towards the pair of electrons that you see here. As a result of which, the bond pair of electrons, instead of being situated at the center, will partially move towards the more electronegative halogen. So this process is called as electron movement. The electrons will be moving in a covalent bond. And why do electrons move? In this example, electronegativity is the reason. But there are so many such examples, so many such reasons due to which the bond pair of electrons in a covalent bond start moving. So today we are talking about those electron movement in the covalent molecules or in the organic molecules. And this electron movement causes a few consequences. There are some effects of this electron movement. So we'll also talk about those effects. That's why the topic is electron displacement and electron displacement effects today. And coming to these two types of covalent bond, the first one is a polar covalent bond, and this is what is observed when you have two unequally electronegative atoms participating in the bonding, two unequally electronegative atoms participating in the bonding, like carbon and halogen, carbon and oxygen, etc. And the second type is non-polar covalent bond. When two atoms of same electronegativity participate in bonding, the bond pair of electrons is exactly situated at the center and all the rules of chemical bonding are followed. That's why you call it as non-polar covalent bond. And we get to see electron displacement in both of them. We get to see electron displacement in polar compounds due to electronegativity difference. And in non-polar compounds, we see it due to various other reasons. There are so many reasons. Reasons like it can be due to presence of a reagent, or it also can be due to presence of some external reasons like availability of a cation in the surroundings or anion in the surroundings, or maybe some other unsuitable reasons. There are so many reasons for this electron displacement. One of them is electronegativity difference, and that causes polar covalent bond. But you get to see electron movement in non-polar covalent bonds also. So let's move to the next page. Let's get started with the topic then. We are going to talk about electron displacement first of all, and after that we'll talk about the effects of this electron displacement. So electron displacement in covalent bond and electron displacement effects in covalent bond. So very first point that we need to cover on is electron displacement happens, but then what are the reasons behind this electron displacement? As we discussed in the last page, one of the reasons is electronegativity difference between the atoms involved in covalent bonding. And the second reason is availability of attacking species around or in atmosphere, attacking species such as electrophiles or nucleophiles or maybe reagents. When you have attacking species like electrophiles, nucleophiles or reagents, these attacking species have capacity to disturb a perfect covalent bond also and lead towards movement of electrons. And third reason is in order to attain better stability. The molecule it itself wants to attain better stability, and in order to attain better stability it will cause movement of electrons. So these are the three possible reasons behind electron displacement in covalent molecules. And now because of this electron displacement in covalent molecules, what consequences do we get to see? What are the effects that we observe due to this electron displacement? The electron displacement effects, there are a few effects and we are going to list them one after other. The very first electron displacement effect is inductive effect. And the second electron displacement effect is resonance. And the third electron displacement effect is resonance effect. Both of them are different. Resonance and resonance effect are two different things. And the fourth one is hyperconjugation. Hyperconjugation and electromeric effect. Alright, so 5 effects. Now in any organic molecule that you observe, the electrons move due to these reasons. And now due to the movement of these electrons, due to any of the reasons, you will see some consequences. But before we could proceed forward, a few points that we need to keep in mind. It's not necessary that every single organic molecule displays these reasons. At the same time, it's not even necessary that every single organic molecule displays these displacement effects. One of the reasons would be observed and maybe one or two of the consequences or effects will be observed. For example, in an organic molecule which is consisting of a carbon-halogen bond. The carbon-halogen bond basically is a polar covalent bond. Because this is a polar covalent bond, you get to see delta negative and delta positive charges over here. So what is the reason behind the movement of electrons here? Electronegativity difference is the reason. Is attacking species is the reason here? No, it's not. The electron movement here is not due to any attacking species. It's not even due to the stability reasons. It's only due to the electronegativity difference. And as a result of this, one of these effects will be observed. Not all of them at the same time or not all of them in the same molecule. I hope that point is clear. Now moving on to the next page wherein we are going to discuss about each of these effects, and we are also going to discuss the reason behind each of these effects in detail. So for now, let's get started with the first effect, which is inductive effect. Inductive effect. So inductive effect basically is one of the most common effects that we get to see in organic molecules. And let us first understand the reason behind inductive effect. What could be the reason? Inductive effect is talking about a consequence observed due to movement of covalent electrons in a molecule. But why did this consequence happen? Why did this effect happen? It happened because that particular molecule was containing a polar covalent bond. That particular molecule was containing a polar covalent bond. As a result of this polar covalent bond, inductive effect was observed. But then why is this polar covalent bond present in that molecule? What is the reason behind polar covalent bond? This polar covalent bond occurs due to presence of two atoms involving in a covalent bond, but the electronegativity of atoms is not same. One of the atoms was having very low electronegativity and the other atoms was having high electronegativity. Because one of the atoms involved in the covalent bond is low electronegative, it will not be able to grab the pair of electrons or keep hold of this bond pair of electrons. That's why the more electronegative atom will be attracting this lone pair, the bond pair of electrons towards it. As a result of this attraction, what happens is the low electronegative atom feels a little electron deficient and experiences delta positive or partial positive charge. And the second atom B experiences a little overpresence of the electrons because the bond pair is more closely existing to this and will be exhibiting slight delta negative charge or partial negative charge. So this partial positive and partial negative charges are causing a polarity in the molecule, are causing a charge separation in the molecule. All right. So because of this low electronegative and high electronegative atoms involving in a covalent bond, because their electronegativity difference is comparatively higher, the polar covalent bond is formed in a molecule. And because polar covalent bond is existing in a molecule, you get to see this partial charge separation. This delta positive and delta negative charges you see, they are because of what? They are because, they cause partial charge separation in the molecule. Because there is a partial charge separation, you get to observe inductive effect. So basically, what is inductive effect? Inductive effect is nothing but this partial charge separation. This charge separation is the consequence, but whose consequence is this? This is the consequence of polar covalent bond. This is the consequence of high electron negativity difference in the given molecule. What if I talk about a molecule where I have a non-polar covalent bond? Like I'm talking about a molecule where there is only a carbon-carbon bond. Because both the atoms in this bond are equally electronegative, because their electronegativity is same to same, the bond pair of electrons is always situated at the center. When the bond pair of electrons is situated at the center, there's no partial positive or negative charges arising over there. So no polarity in this molecule. But if there is no polarity, no inductive effect, because inductive effect is nothing but polarity. This inductive effect is nothing but creation of partial positive and negative charges. Partial charges creation in a organic molecule is called as inductive effect. So if you are having this inductive effect, if you are having a partial positive and negative charge created in the molecule, that must be due to electronegativity, and you won't get to see inductive effect when you are having molecules which are containing only non-polar covalent bonds. So inductive effect basically is causing partial positive and partial negative charges. To understand this better, let's take an example of an actual organic molecule. Imagine I'm talking about CH3Cl, methyl chloride. So in this molecule, let me elaborately display the chemical bonds that we have. We have a bond between carbon and chlorine, and at the same time there are 3 bonds for this carbon with 3 different hydrogen atoms. Now I'm just trying to analyze these all bonds. I'm analyzing the bond between carbon and hydrogen 1, hydrogen 2, hydrogen 3. Basically, carbon and hydrogen, their electronegativity is very close to each other. There is very less difference between the electronegativities. Due to this very close by electronegativity, the bond pair of electrons will be situated at the center. So they lead to formation of a non-polar covalent bond. Because the bond is a non-polar covalent bond, I don't get to see any charge separation in the first bond, the second bond and the third bond formed by the carbon. But when I observe the case of chlorine, in case of chlorine is more electronegative. Its electronegativity is very high in comparison to carbon. Because of this high electronegativity, what happens is chlorine starts attracting the bond pair of electrons towards itself. And as a result of this attraction, the bond pair of electrons will slightly move towards chlorine, and they get situated adjacent to chlorine instead of being at the middle of carbon and chlorine. So now carbon partially is experiencing electron deficiency. The pair of electrons that you see here are not permanently taken away by chlorine. Chlorine still is involved in bonding, but it is slightly over enjoying the presence of electrons. That's why chlorine will be experiencing a little extra negative charge. You call it as partial negative charge, and the symbol is called as delta. So you represent it as delta negative. Now on other hand, carbon, because electron pair, the bond pair of electrons have moved a little apart from carbon, it will experience electron deficiency. It will experience delta positive charge. So this delta positive charge of carbon and delta negative charge of chlorine are arising due to the electronegativity difference. Between carbon and halogen, the electronegativity difference is comparatively higher. Because electronegativity difference is higher, you get to see movement of electrons, and because electrons are moving, you get to observe polarity over here, and existence of polarity is nothing but existence of inductive effect. Inductive effect is just partial charge separation, right? So there is inductive effect observed between carbon and chlorine in this molecule methyl chloride. So in methyl chloride CH3Cl, the carbon chlorine bond experiences charge separation. delta negative here and delta positive here. So this molecule is exhibiting inductive effect. This molecule has what? It has got inductive effect. We by now have understood what exactly is inductive effect, what is the reason behind inductive effect. So just as a quick recap, inductive effect is charge separation in the given organic molecule due to presence of a polar covalent bond, and the reason behind inductive effect is presence of a polar covalent bond, right? So now what are the points can we understand about this inductive effect? Let us take more examples to understand more properties of this inductive effect. Observe this example. I'm talking about CH3CH2Cl. In the last page, when we have taken example of CH3Cl, I told you that this carbon is having a delta positive charge and this chlorine is having a delta negative charge. Now, the carbon which is directly connected to the functional group is regarded as alpha carbon. When you have more carbons in the molecule, just for the sake of identification, let us name the carbons as alpha, beta. Alpha carbon is the carbon which is directly connected to the functional group. Beta carbon is the carbon which is connected to the alpha carbon. Gamma carbon is the carbon which is connected to the beta carbon. Alright. And if you have fourth carbon, you can name it as delta. Delta carbon is the carbon connected to gamma carbon. This naming is only for the sake of better understanding and to avoid confusions in large molecules. So over here, since I have two carbons, instead of getting confused, I'll just name it as alpha carbon, the carbon which is directly connected to the functional group chlorine, and the carbon which is connected to alpha carbon is called as beta carbon. So I have alpha carbon and beta carbon over here. When I elaborate the bonding in this alpha carbon and beta carbon to understand if there is any inductive effect observed over here, I notice that the bond between the carbon, alpha carbon and the chlorine is a polar covalent bond. And due to this, there is a delta negative charge on chlorine, there is a delta positive charge on carbon. And the rest of the valencies are filled by hydrogens like this. So it is CH3, CH2Cl in which the alpha carbon is experiencing inductive effect or is experiencing partial charge. Now because this alpha carbon is the one which is directly connected to the negatively charged or this partial negative charge functional group, the effect or the inductive effect is maximum over here. The inductive effect is maximum on this particular carbon. But why is it maximum? Because this is the carbon which is experiencing this electron deficiency. This is the carbon which is present right next to the functional group. So its experience will be higher. Fine, it is experiencing highest inductive effect. Fine, then now because of this inductive effect, this particular carbon, this particular alpha carbon is behaving electron deficient. It has become electron deficient, right? So now because this particular alpha carbon is electron deficient, what does it do? Any electron deficient species will develop a positive charge like this, or at least a partial positive charge. But presence of any positive charge or a negative charge or a partial positive charge or partial negative charge is not stability. Any species which is experiencing electron deficiency would always try to nullify the charge that it has developed. It will always try and reduce the charge or neutralize the charge that it have developed. Now this alpha carbon have developed a positive charge and it wants to nullify it to attain better stability. But how can a positive charge be nullified? How can a positive charge be neutralized? It can be neutralized by adding a little more electron cloud or giving a little more presence of the electron. So this carbon, because it is electron deficient, because it is trying to nullify the positive charge that it have acquired, it will try to grab electron cloud or it will try to grab electrons presence, all right? But then where can it get electrons from? It has got a few options. Let us observe the options. Option number 1, it can get the electron from here, from chlorine. But that is not possible. Why? Because chlorine is more electronegative. Under no circumstances it will let the electron move towards carbon. So this option is lost. And now second option is this carbon can try to grab electrons from hydrogens. Fine. And third option is it can try to grab electrons from carbon. So there are two options left. Carbon can take electrons from hydrogens. Carbon can take electrons from adjacent carbon. Now, out of these two options, which option should this alpha carbon choose in order to neutralize its charge, in order to neutralize its positive charge, partial positive charge? Whichever is easier option, it will choose that. So which is easy now? Is it easy to grab electrons from hydrogen or is it easy to grab electrons from carbon? My answer is it is easy to grab electrons from carbon. But why? Because in case of hydrogen, you have got only one shell, one S shell, which is closest to the nucleus. It is experiencing high nuclear charge. So electron of hydrogen is tightly bound to its own nucleus. So it's not easy to take electrons from hydrogen. So hydrogen का जो भी option है, it's lost. Now hydrogen cannot help you to nullify the charge present on this alpha carbon. So only option left is to get it from carbon. So let us quickly repeat this point. The alpha carbon that you are observing over here is experiencing inductive effect. Due to inductive effect, there is a partial positive charge developed on it, and due to presence of this partial positive charge, it behaves a little unstable. Presence of positive or negative charges are not stable, so it behaves a little unstable. And now in order to rectify that instability, in order to achieve better stability, it would be trying to grab electrons and it would be trying to neutralize its own charge. And how can it grab electrons? You can take electrons from chlorine, but that's not possible because chlorine is more electronegative. It can try taking electrons from hydrogen, but that is also not possible because hydrogen's nuclear charge is higher. So electrons cannot be taken from hydrogen. The only option left now is carbon, the adjacent carbon. So this alpha carbon will now try to take electrons from this beta carbon. The alpha carbon, which is delta positive, which is electron deficient, will now try and absorb the bond pair of electrons of this beta carbon towards it a little. But now if you ask me, carbons are equally electronegative. How is this happening? They are equally electronegative when tested individually. Now that you are observing in a molecule, and in this molecule, this particular alpha carbon is already experiencing electron deficiency, it behaves more electronegative. So alpha carbon is more electronegative in this case because of electron deficiency, and this is the result of inductive effect. And now in order to rectify this electron deficiency, a pair of electrons has been grabbed from this particular beta carbon. But then the point is, can this alpha carbon pull the beta carbon's electrons as good as the chlorine have done? No. When you compare the capacity of alpha carbon to take the electrons or grab the electrons towards itself, it's lesser than that of chlorine, but to some extent it will manage. And as a result of this, what happens is you get to see a little charge developed on this beta carbon also. So the conclusion is, if I'm talking about this molecule CH3 single bond CH2 single bond chlorine, chlorine is highly electronegative. As a result of this, it will be developing a delta negative charge because it absorbs or it will attract the bond pair of electrons more towards it. And now due to this, there will be a delta positive charge on alpha carbon, and you call this as inductive effect. Inductive effect is maximum on alpha carbon, but then because of this inductive effect, alpha carbon have become a little unstable. To attain stability, it will try grabbing the electrons of beta carbon. It won't be able to completely attract the electrons towards itself, but it will manage to some extent. And due to this beta carbon now will develop a little positive charge. So there will be effect of inductive effect on beta carbon also. The consequence of this inductive effect is experienced by beta carbon also. But now if I compare alpha carbon and beta carbon in terms of the effect of polarity or the inductive effect, alpha carbon is much more affected. The inductive effect is maximum experienced by alpha carbon, and then is beta carbon. What if I have the gamma carbon, then it goes to gamma carbon. What if I have delta carbon, then it goes to delta carbon. So the conclusion of this page is, if you are having inductive effect observed in a molecule, this inductive effect does not only affect the alpha carbon. If there is a beta carbon, it will affect the beta carbon as well. If there is a gamma carbon and delta carbon, it will affect those carbons as well. So the inductive effect is not only for one carbon, it's for all the carbons that are present in a sequence, that are present in a row. So now, we spoke about inductive effect being observed in alpha, beta, gamma, delta carbons, and we also have given the order that inductive effect is maximum in alpha, then it goes on reducing as you move away from the alpha carbon. This inductive effect that you're working on is classified into two types. Inductive effect can be classified into two types. Based on what? To understand that, we have to take one example. So let us stick to the same example that we have taken in the last page. I'm talking about ethyl chloride. And in ethyl chloride, this particular chlorine is having high electronegativity, and as a result of this, chlorine will be experiencing delta negative charge. And here is alpha carbon, here is beta carbon. Delta positive charge has got utmost effect on alpha carbon, so I'm considering alpha carbon for now. Now what should we observe? This inductive effect, when I observe the effect overall, I see it being delta positive and delta negative. So inductive effect is observed in positive, in negative as well. There's one atom which is a more electronegative atom. In terms of this particular atom, inductive effect is negative. There's another atom whose electronegativity is lower, and in terms of this particular atom, the inductive effect is positive. So basically we can classify inductive effect into two types. One is plus I effect, which is in terms of the low electronegative atom involved in the process, and the other one is minus I effect, which is in terms of the more electronegative atom involved in the process. So inductive effect can be positive inductive effect, it can be negative inductive effect. But always remember, there are both positive and negative effects observed in a molecule. When you look at a molecule, there's a plus I effect, there's a minus I effect, right? And minus I effect is always in terms of the high electronegative atom, and plus I effect is always in terms of low electronegative atom. So the high electronegative atoms which cause minus I effect are generally called as minus I groups, and the low electronegative atoms which generally cause plus I effect are called as plus I groups. So if the group is minus I or plus I, basically depends upon the counterpart. For example, over here, if I have to talk about the bond between carbon and chlorine. Between carbon and chlorine, chlorine is minus I. But if I talk about the bond between chlorine and fluorine, fluorine is more electronegative, isn't it? So it would be pulling the bond pair of electrons more towards itself. So fluorine will be minus I over here, and chlorine behaves plus I. So there is no constraint that some groups are plus I and some groups are minus I forever. The plus I nature or the minus I nature basically depends upon the strength, the electronegativities of the atoms involved in that particular chemical bond, in that particular covalent bond. But in general, if you have to observe, there are a few plus I groups. Alkyl groups basically act as plus I groups, and the functional groups like halogens act as minus I groups. Alright, this is just for the sake of an idea of the plus I groups and the minus I groups. But they might vary. It's not that carbon is always plus I. No, it's not that. Carbon can behave minus I based on the counterpart. Similarly, any group can be plus I, any group can be minus I. So what do we generally do is we write the order of inductive effect. The first order is talking about minus I effect. So in minus I effect, hydrogen is considered as standard. In plus I effect also, hydrogen is considered as standard. Alright. So keeping hydrogen at the center, we are comparing the plus I effect of the groups and minus I effect of the groups. Okay. So let us observe the plus I effect first of all. Generally, the alkyl groups are plus I groups. The alkyl groups in general are plus I groups. So let us look at the first one. Methyl group is a plus I group. But then, than methyl group, ethyl group has got a better plus I effect. Basically, it's like more carbon atoms in the chain, more is the plus I effect. When you look at the next one, it's propyl. There are 3 carbon atoms altogether. This has got better plus I effect than ethyl. When the number of carbon atoms increased to 4, the plus I effect further increased. So the plus I effect goes on increasing as the number of carbon atoms or the number of methyl groups increase. So it is methyl, and then ethyl group that you see here can be referred as primary, and then is secondary, and then is tertiary alkyl group. This is the plus I effect. The primary alkyl group has got lower plus I effect than secondary alkyl group and then tertiary alkyl group. Okay? And when you look at negative inductive effect, so here are the groups which have got greater minus I effect than hydrogen. And here are the groups which have got greater plus I effect than hydrogen. Now, if you are confused about how can hydrogen be in both the places, as I told you, every group has got a little plus I effect and every group has got a little minus I effect. The plus I effect or minus I effect depends upon the counter atom that is involved in bonding. Hydrogen can be plus I based on what do you have adjacent to hydrogen. Hydrogen can be minus I based on what do you have adjacent to hydrogen, right? So the groups which you see for minus I effect, let us look at the groups right from here, right from adjacent to hydrogen. The first one is phenyl. This is nothing but phenyl. If benzene is acting as a side chain, we represent it as C6H5. Phenyl group has got the least minus I effect in the entire list, followed by amine. NH2 group is amine group, and then alkoxy. OR group is alkoxy group, and then is hydroxy. OH group is hydroxy group, and then comes halogens, and then comes the rest of the functional groups. But if you notice something over here, halogens which are very much electronegative are having less minus I effect, which means you have better minus I effect, better groups which can pull the electrons towards themselves than halogen. We generally tend to assume that halogens are very much electronegative. Yes, they are. They are very much electronegative when you compare amongst the elements. But when you look at the functional groups like amide functional group, acyl chloride group, carboxylic group, carbon monoxide, aldehyde, etc. groups, the halogens are less minus I groups than all of these functional groups. And it's important you learn this order if you're preparing for competitives. For boards, it is not necessary. For annual exams in the schools, this order is not mandatory. Just learn a few groups as examples for minus I, as examples for plus I if you're preparing for class 11 annual exam. So this is about inductive effect. Let us quickly recap whatever we have learned over here. So we are working on electron displacements and the effects of electron displacement. The electron displacement is observed in organic molecules, in covalent molecules basically, and the reasons behind electron displacement, there are multiple reasons, of which one could be electronegativity difference between the atoms that are involved in covalent bond, or it also can be the attacking species, presence of electrophile, nucleophile or reagent in the atmosphere. It also could be stability reasons. And now because of any of these reasons, if you see electron displacement in the molecule, one of these effects can be observed, one of these consequences can be observed. The first one is what we discussed till now, which is inductive effect. Inductive effect is basically caused due to electronegativity difference. When you see electronegativity difference between the atoms involved in covalent bond, you see inductive effect. And inductive effect basically is observed in case of a polar covalent bond due to the more electronegative atom pulling the bond pair of electrons towards itself, and it results in development of a partial positive and negative charge. So this partial charge development is nothing but inductive effect. Inductive effect or creation of partial charges is same, and this inductive effect is represented as delta positive and delta negative. Delta positive for the atom involving in the atom which is losing electrons or which is not able to attract electrons strongly, and delta negative is for the atom which is able to attract more strongly towards itself. And this inductive effect is not only effect on alpha carbon, even the beta carbon, gamma carbon will be affected towards it. But then alpha carbon experiences the maximum effect, and as you move away from alpha carbon, the effect, the strength of the effect goes on decreasing. And on the other hand, this inductive effect can be classified into two types. One is plus I effect and then is minus I effect. Plus I is in terms of low electronegative element involved in bonding. Minus I is in terms of high electronegative element involved in bonding. And here are some examples of plus I groups and minus I groups and the order. So this is what is all about inductive effect. This is what you need to know for class 11 annual exams.